can use all of these numbers to calculate the standard deviation for the two populations, because you're making this if you accept the assumption that the standard deviations for the two populations are the same to start off with. Okay, then you can use 44 numbers or 42 numbers instead of 20 numbers or 22 numbers to estimate the standard deviation, so you get a better estimate. Okay, so there's a lot of things going on here, right? So now I'm going to do this exact same thing. I'm going to do it in SPSS. Now SPSS doesn't like the idea that we put these in two columns, except in one situation. We're going to see that situation shortly. Okay, I'm going to copy these guys out here. I'm going to cut that. Oops, cut that, and I'm going to paste it here after the 53. Okay, I'm going to put twos down here. Oops. Edit, fill, down, put all twos in there. I'm going to put all in ones in here. Edit, oops, fill down, okay. And instead here is going to be the amount of time elapsed, time guess, okay. And over here I'm going to put smoking status. Okay, and you guys going to remember that 1 represents smokers and 2 represents non-smokers. I'm going to save this. Okay, for SPSS, so I know which one it is. Okay, and now when I import this into SPSS, I'm going to have a different situation. I'm going to be able to work with this effectively. Okay, I think on a test you can probably pretty much assume that the data will be given to you in a form that you're not going to have to do too much manipulation like I'm doing right now, but I want to show you that like there's differences in the way SPSS handles data. SPSS, even though it looks like a spreadsheet, is not a spreadsheet by any means. Okay, I need to change this to Excel, be able to see the Excel files, and I think that this is the Excel file I was just working with here. Yeah, I believe so. Okay, oops. Oh, it won't open it because, anyone might take a guess why it won't open it? Because I must still have it open in here. Okay, it doesn't like to share data files. Let's try again. Open, data. See if that was what the problem was. Excel. Is it that one? I think it's this one. I think it's this one. Okay, yep, that's the one. And there it is. If I want, I can go into variable view and I can take the smoking status, and in the values, I can say 1 was smokers and 2 was non-smokers. Okay, so that when the tables print out, it'll have those values instead of 1 and 2. You can see it changed it here. I could view that with the values, or just the numbers, or I could view it without. Doesn't change anything. It's just the way it's viewed. Okay, so now I'm going to do my analysis. Analyze, compare means. Again, what am I going to pick here? Not one sample t-test, there's 2 samples. Not paired samples because they're independent samples. They're not related to each other. Independent samples t-test. So now I'm going to put my test variable, which is the mean, what we're calculating the means of, which is the time that they're guessing, and the grouping variable. In other words, group 1, group 2, that's the smoking status, whether they're smokers or not smokers. So that goes down there. I know the grouping variable goes down here because those are the groups that I wanted to break it up into, right? So I know that the other variable has to go up there. Now, SPSS is a little lazy here. It requires that you define the groups by telling it how they're input here. We know group 1 is defined by 1 and group 2 is defined by 2. Okay, it's a little silly since there's only 2 groups there. You'd think it'd be able to do it itself, but it forces you to do that. I'm going to click OK, and it calculates it for us. And what do we have? We have a t-score of 2.589. Looks familiar, correct? That t-score of 2.589 represents a two-tailed significance or p-value of 0.01, 1.3%. Exactly the same thing that we got when we performed this test using Excel. Okay, so now what we're doing here is, I'm going to go back to our Word document in here, and we could actually go back to the PDF file from the lecture earlier this evening, and you'll find that there are formulas that you have for calculating a t-score and hence a probability. You could use, remember, you can use, if your sample size is large, you can go to Z-table and actually calculate a to estimate a p-value, right? Really, all you're interested in is whether or not you get a t-value that's big enough to say you're 95% certain you can reject the null hypothesis, or 5% chance, less than 5% chance of being wrong. So you want that t-value for that number of degrees of freedom to be big enough to be bigger than what you need in the table that we in the t-table. But t-table doesn't calculate a p-value for you. Excel will, SPSS will. And you can on your own if your sample size is large enough. Okay, so let's see what we have here. We have uh, we have formulas that allow us to calculate what the t-value is based on the difference between the two means, mean 1 minus mean 2, right? We're calculating difference in standard deviations. This is your standard error on the bottom. Difference between the two values, the two means, over your standard error. In this case, this represents a pooled standard deviation, a standard deviation that combines the two of them. And that's calculated this way. It's really basically a weighted average of the standard deviation of the two groups. Okay, so we have situations here where you can have one sample, compare it to a value. You can, or you can have proportion. You can have two samples, one sample compare it to value, two samples that could have equal variances, equal or unequal size, two samples that have unequal variance, right? So you can't assume that the same variance, and you're using another formula for calculating the t-value for situations where you have two samples with unequal variances. Very complicated, not a very complicated formula here. X1, group 1 mean minus group 2 mean, divided by the standard error, which in this case for unequal variation is the square root of the standard deviation square group 1 over the sample size of group 1 plus the standard deviation group 2 squared over the sample size of group 2. And take the square, add them together, take square root of the whole thing. That'll give you your t-value, and you can figure out whether or not that t-value is big enough, or z-value, if you got big enough samples, is big enough for you to reject your null hypothesis. In this particular case, with unequal variation, calculating the t-value and the standard error is relatively simple, but calculating the degrees of freedom, this Greek letter nu, that's nu, this Greek letter nu represents the number of degrees of freedom. That's very complicated, right? And it's so complicated that either most people use Excel, SPSS or Excel or some other program to calculate the t-score for this in this situation, or they just take the sample size of the smaller group and use that as a conservative estimate of the degrees of freedom. Right, small estimates, very conservative. Okay, you lose the advantage of being able to combine those two sample sizes. Okay, that was I really gave you kind of a mouthful here, right? So I just want to back up a little bit, see if I've completely lost you guys yet or not. Okay, independent. Can't have it open. I'm not sure what that refers to. Okay, I'm going to move on. Okay, so let me take a look at that. We calculated in that in SPSS. Now I'm going to move on to the next problem in that Word document. Let's see if I can't find it ever again. Okay, where is it? Let's see. I'll open it this way. Okay, here we go. Let's go back here. Okay, second problem. Okay, the following recipes both taste great, but you want to see whether they pack the same amount of is that calories or salt? Calories. Okay, is recipe number one, made by recipe number one followed by 5 cooks, recipe number two followed by 5 cooks, supposedly the same calorie count, but we want to know if there's some variability, because if they get different calorie counts just because of the way cooks tend to interpret the recipes or something like that. I don't know. It's just a group of numbers really for us to do this with. Okay, first, what's our assumption? Independent samples. They're roughly normally distributed. What's your null hypothesis? Our null hypothesis is the mean number of calories for recipe 1 is equal to mean number of calories for recipe 2. Our alternative hypothesis is that the mean number of calories of 1 is different than the mean number of calories of 2. Okay, it's very small sample size, so I'm not too optimistic about this, right? Normally you need big sample sizes. So I'm going to do this in Excel and SPSS. Okay, we're going to calculate our t-value on our p-value, our probability, even though I don't have a whole lot of faith in this being a really significant result. Okay, I'm going to save that, and I'm going to open. Okay, that's problem number 2. Okay, here they are. Here's the numbers here. Let's blow them up a little bit so we can see them a little bit better. Okay, let's do our t-test. Remember, the t-test is going to give us let me do it this way. I'm going to do it this way so I can get the help file in case I need it. Okay, here's our help file in case we need it. Okay, so now array number 1 is going to be recipe number 1. Array number 2 is going to be the values for number 2. Two-tailed test. We can do a one-tailed test if we have reason to believe that there's no other outcome but that one is bigger than the other, and the type of test that we're doing here. Okay, t-test 1 paired. Let's see, type of data paired. No, it's not a paired, right? Because not the same chef doing it with recipe number 1 and recipe number 2. It's 2 different chefs. The problem didn't say anything about being the same chef or these being paired. So these 10 different chefs are doing this recipe. Okay, and so we're not going to do paired. So it's not going to be a 1. 2 is equal variances. I'm okay with that for the moment. 3 is unequal variances. So I'm going to say equal variances just for the hell of us. SPSS will actually help us out on that. Okay, so our p-value is 0.81. There's really not much, that's not much to say there. It's way bigger than 0.05. We have an 81% chance of being wrong if we say that there's a difference between group 1 and group 2 in terms of like the entire population mean. Okay, that would be a t-score. See, t inverse. Okay, let's see, that's the p-value, and I'm going to say that I'm going to say 8 degrees of freedom. Okay, that's going to be a t-score. It's really small, right? It's not much reason to believe that we could say that these two groups are really different from one another. We can even look at it and see that we wouldn't have much success with that. Let's move on to the next one, see what that one looks like. Okay, let's open. Okay, and I'm going to open problem number 3. Okay, so now this one represents a situation where, see how to read this one. Here's problem number 3, 2. Oh, I lost track of it. I may not have this one. I may not have this one on these pages. Oh, there it is. Okay, t-test. Nope, I don't have that. I don't have this one. Matter of fact, I'm going to avoid that one entirely. I am going to go to problem number 4. That's a little short on time. And problem number 4 is a little bit more significant for us. Okay, let's take problem number 4. Problem number 4 represents a weight loss program. We're trying to decide whether a weight loss program is effective. Okay, and we have 2 through 17. That would be 16 people that participate